Hello everyone, and welcome to the first video in the series for thermodynamics at RIT. My name is Mike Schertzer, and I'll be the professor that's kind of leading you through your journey to understanding the universe through the lens of thermodynamics as a mechanical engineer. Now, we have a couple videos here that are prep work for the course, so these videos hopefully are something that you're watching before you even sort of have your first lecture with me. Now, I think most of these sort of prep work videos are going to be talking about definitions of terms so that we all have the same vocabulary or maybe nomenclature as we're beginning the course. I think most professions are like this, where you sort of have this decoder ring, in our case an engineering decoder ring, where you need to be able to understand some of the terms that people are using as they're working in your field. Now, what we're going to focus on today is the definition, the difference in the definition between mass and weight. So I guess the first definition that we'll talk about is thermodynamics itself, right? So that's the name of the course, and it's a compound word from two different Greek words, right? So the first is thermo. So thermo is the Greek word for heat. The second word is dynamics, which is the Greek word for force. So when you put these two things together, thermodynamics, what that really means is this is the study of how to get force from heat. So as mechanical engineers, a lot of times we're interested in generating heat, maybe by burning different types of fuel. If you look at the definition in the dictionary, it might say something like this: that thermodynamics is the engineering analysis of thermally driven or heat-forced systems and their interactions with their surroundings. Right? And that's kind of a very technical definition. And you might wonder, like, why do I care? Why should I care? Right? And I think in this course, we're going to learn first about how we can use heat to create work, right? So it's going to be about transfer of energy. But I think even more than that, we're going to learn about fundamental principles that you can use throughout your whole engineering career to help you design and build practical systems. So for a long time, as a mechanical engineer, if someone said like, oh, I can burn something to make heat, what you might have said as a mechanical engineer, and what we still do a lot of, is like, oh, how can I use that heat to boil water, right? And when you think of this, maybe you think about a steam engine, right? And in a steam engine, what I think about is there's some operator who's shoveling coal into a boiler, right? And we're burning that coal on a locomotive in order to boil water. And the reason we like to boil water is because water's pretty dense, but steam is 1,000 times less dense. So what happens is those water molecules, when you boil water, vigorously separate, right? And the spacing between those molecules is much bigger. So you get this rapid expansion of water as it moves from a liquid to a vapor. Now, what's really, really cool is that as mechanical engineers, we figured that if we sort of had that transition of phase happen across a turbine blade, which is sort of like, if you think about a fan blade, maybe the fan blade that's used to cool your computer, right? A turbine's kind of like that, but it operates in reverse. So we have this liquid water that's expanding into steam, and we force it over the blades of that fan or that turbine, and that causes the turbine to spin around, right? And that can make the mechanical work, because now the center of that fan, we have a shaft that's attached to that, and now it's spinning because the blades of the fan are moving. And if we're friends with an electrical engineer, maybe we attach that spinning shaft to some kind of generator, and we turn that mechanical energy into electrical energy. So one of the reasons that we care a lot about thermodynamics and mechanical engineering is because this is how we go from heat energy to mechanical energy, ultimately to electrical energy. Now, this is something that we still do today. It's not something that's limited just to locomotives. right? And the steam age, this is something that we do today in coal-fired power plants. It's something that we do in nuclear power plants. I remember when I first learned that, it seemed, on one hand, kind of disappointing because we think about nuclear energy as being some kind of space age or Star Trek level technology. And it really is amazing. But ultimately, what we do with that nuclear reaction is we noticed, man, it generates a lot of heat. And some mechanical engineer came by and said, oh, I bet you if I use that heat, I could boil some water and make some steam, right? And we do that and we can generate power with that. So a lot of what we'll talk about in thermodynamics is doing this, but this is not the only way we generate power from heat, right? Because, if you drove a car anytime today, right? I was going to say to work, but, this is 2020 in May, so we're not really driving cars to work right now. But if you were driving your car or a motorcycle, then, you're creating heat by burning gasoline and, you're not boiling water. You don't have to fill your tank up with water to do that, right? So in thermodynamics, we care about this because it's very practical, right? So we're going to learn how auto engines work. We're going to learn how coal-fired and nuclear-fired power plants work. We're going to learn how we can sort of take similar principles and make natural gas power plants, or use that same idea we use for a natural gas power plant to make a jet engine, so we can get this, enormous plane, which is certainly heavier than air, but how do we make it fly, right? And we can do that through principles that we learn here in thermodynamics. And, these first three things that we're talking about, right, we're taking heat and turning that into energy. But the last kind of device we'll talk about is a temperature control device. So something like maybe the air conditioner in your house, or maybe a refrigerator in your house. And these devices are interesting. We're going to use the same principles that we use in the rest of these heat engines, but we're going to kind of turn it on its head. And when we do that, we're going to be able to sort of trick the universe to transfer heat from a place that's cold, like the middle of your freezer, to a place that's relatively hot, right? Like the space in behind your freezer or your fridge where the heat gets exhausted in that system. I also, in this class, I want you to learn one of the sort of, I think, truisms or maxims of engineering, and that's that the process is more important than the result. Because you can get a good result sometimes just by lucking into it. But if you have a robust process, a process that you trust, a process that's systematic, and you consistently implement that process, you're going to get more good results over the long run. And that's really what we're trying to do as engineers, because a lot of the decisions that we make have real societal implications. And we want to do the very best we can to arrive at solutions that are helping people and that don't backfire and hurt people. I want you to learn that mass itself has energy. So throughout high school and maybe first year physics, you learn about conservation of energy. And a lot of times that's in sort of roller coaster or cannonball type project or problems where you're transferring energy between maybe gravitational potential energy and kinetic energy. In this class, it's all about energy conversion because we're going from sort of heat energy to mechanical energy and maybe back again, but we're going to do it in a different way. We're going to learn that some particular mass of steam has energy. And how does that energy change as we cool that steam back into water, or as we take that liquid water and boil it back into steam? And I guess the real reason as engineers that we want to understand things is because ultimately we kind of want to try to bend the universe to our will, right? So we want to be able to control complicated systems, but before we can do that, we need to understand them. And we're going to learn kind of a modular design process that will help us to understand these systems that we'll talk about so that we can design or control the output from these complicated processes. I guess I also want you to learn that the thermal's just awesome, right? So we're going to take this kind of modular idea where we can understand individual parts of a process, and then we can put those parts together like Lego blocks to do some really cool things, right? Like build power plants, cars, airplanes, or air conditioners. So when we talk about a systematic process, right, like I said, this is really about how do we increase our chances of getting more positive results over the long term, right? And I think one of the really big parts of that, as we're working through problems in this class and throughout your entire engineering career, is to track units, right? To understand units and dimensions, right? So we really need to be using, when we're doing any kind of math, first we need to understand what's the difference between a dimension and a unit. And then when we're doing calculations, we really have to be aware of the units that we're using so that we're not making huge mistakes, sometimes off by factors of 10, which we call orders of magnitude, if we just mess up the units, right? And because we're humans, as we're working through problems, we're going to make mistakes, right? Humans do that. But if we have a good process in place, we'll catch more of the mistakes that we make than if we didn't have a good process, right? And one of the components of our process is checking units as we're working through problems. And when we do this, it's almost like you're cheating on a test, because a lot of times if you make a mistake, you can see that you've made a mistake when you track the units, right? So when I talk about unit tracking, it's one of these things where you can prove that you're wrong. You can't prove that you're right, but you can show that you're wrong, right? And that's half the battle, right? It's really important to have these systems in place, right? So a good system will give us good results more often than not, right? And that's why we care about tracking units and understanding dimensions, right? So here's an example, right? So here I'm trying to calculate torque, right? So you probably remember this from university physics, right? Maybe even high school physics, that torque, right, or moments are force times distance. So if you're using metric units, right, which are certainly more sensible than imperial units, then you know that torque is in the units of Newton meters, right? And this is maybe trivial, but here, right, you know that to do this, you take a force multiplied by a moment arm, right, or a radius, right? And you can see that if I take newtons times meters, I get Newton meters, right? So here you can see from the equation that you need to get the right units, right? Now this one's kind of trivial because we're not doing any kinds of conversions, right? A lot of times if you have mass in there, you might have to use Newton's second law to sort of convert that mass into force, right? But we'll see how to do that as we move through. Right, now I've been talking about units and dimensions, and maybe it's important to understand the difference, right? So a dimension is the quantity that's being measured, right? So maybe I'm trying to find the length of something, right? So length is a dimension, right? Now I can measure that length in any number of different ways. I can use inches or centimeters. I can use, feet. I can use, non-standard measurements like hand spans or something, right? And as I pick how I'm going to quantify that length, that's my unit, right? Now, I think in this class, if you haven't already, you will come to the realization that the rest of the world has it right, that SI units are much, much better than imperial units or feet and inches. Right now, you probably hear throughout this course, right? I was born in Canada, so I was kind of indoctrinated into the SI system. So maybe I'm biased here. But I think as engineers, we'll come to see pretty quickly the benefits of the metric system. But because we live in the United States, and the United States makes up something like 50% of the global economy, it's really important that we know how to do problems in the imperial unit system. Now, again, maybe because I was born in Canada, we call it the imperial system, so we can blame the British. But here in the U.S., where you might not like the affiliation with the Brits, it's sometimes called the U.S. customary system, or USCS, right? And the metric is sometimes called SI units, right? Even though it's the international system, right? But the SI units were made, sort of popularized by the French. So it's really a system international, right? So it's kind of, the words get inverted, and that's why it's the SI system. So here's a simple chart, and it kind of shows us the difference between a dimension and a unit, right? So here in the leftmost column, we can see different quantities, right? Or dimensions like length or mass, right? So in SI units, length we might quantify by meters. Mass we might quantify by kilograms, right? Whereas in the imperial system, in distance or length, you're talking about feet. But in mass, you're talking about pounds, right? Now, this is one of the confusing things that we'll talk about. You sort of have to talk about this as being pounds mass because the imperial system is maybe not as sensible as the SI system. You also talk about forces in terms of pounds, right? So there's a difference between pounds mass and pounds force, right? And we don't have that same sort of issue in the SI system where we talk about mass in grams or kilograms and force in newtons, right? So the next thing we want to talk about here is mass versus weight, right? So mass and weight can be confused, less so in SI units, and certainly often in imperial units, right? So how do we define force, right? So we didn't know about forces really until Newton, and that's sort of the advantage that the SI unit has, is because it's newer, right? So this came about, before we realized that force and mass were, different things, right? So Newton told us that force is equal to mass times something's acceleration. So how fast the velocity is changing with time. Right? Whereas mass is kind of a measure of how much stuff you have, right? So weight is also kind of a measure of how much stuff you have. This is like the weight is the force that's exerted on a mass due to gravitational acceleration, right? And again, SI has the advantage of sort of being implemented after we understood all this physics, right? But the imperial system was around before any of these ideas existed. So they didn't have they didn't get the benefit of foresight when defining the difference between mass and weight. So I think mass and weight and the differences between them are more straightforward when we're using SI units. And that's because, like we said, mass has a separate unit, kilograms, from weight, which is newtons, right? Because mass is about how much stuff you have and weight is about force. Right? So, in a lot of things in physics, we're certainly grateful to Isaac Newton, but he told us, right? He found this sort of relationship that 1 Newton is the force that you get when you take 1 kilogram and it's accelerating at 1 meter per second squared. And this is a great relationship to remember because sometimes when we're doing unit conversions, we'll need to convert between force and mass. And we do that just by remembering Newton's second law, which is written out here. Now, mass and weight, it's kind of a bear to deal with when you're talking about imperial units, right? And that's because, on the surface, these things seem like they have the same units, right? Because mass is in pounds and weight is in pounds, right? So here we have a subscript, right? Mass is in pounds mass and weight is in pounds force. And the problem here is that the difference between mass and weight, we really only understood it after we already had the imperial system, right? So what they did was they tried to shoehorn the idea of mass into the imperial system, right? And the way they did that was they said, oh, well, this is easy since most of humans' lives will be spent here on Earth where we're subject to gravitational acceleration, which doesn't really change very much from sort of the top of Mount Everest to the bottom of the Marianas Trench, right? Gravitational acceleration is generally constant here on Earth. So we'll say that 1 pound force is the amount of force that 1 pound mass exerts or receives when it encounters gravitational acceleration. Right? So you can't use the version of Newton's second law that we're all familiar with when we're talking about imperial units. Because in imperial units, weight does not equal mass times gravitational acceleration. Right? And we can see that here because gravitational acceleration in imperial units is about 32 feet per second squared. Right? Now, I don't need my calculator to tell me that 1 pound force does not equal 1 times 32.2. Right? This math doesn't work. Right? So what we need to do is not talk about a gravitational acceleration, but talk about a relative gravitational acceleration. Right? So 1 pound force is defined as being the force exerted on 1 pound mass when it encounters gravitational acceleration. So here on Earth. Right? So gravitational acceleration is already built into this equation. So weight is equal to mass, at least the magnitude of these properties are equal if you're on Earth experiencing gravitational acceleration. Right? So 1 pound force is what you get when you have 1 pound mass sitting on the Earth's surface. So we know that gravitational acceleration is about 32.2 feet per second squared. Right? Now, you might go up to the moon and you'd have a very different sort of local gravitational acceleration. Right? So we need to be able to see what would happen on the moon when the gravitational acceleration goes down. Right? So now we got to think not about a absolute gravitational acceleration, but gravitational acceleration relative to the gravitational acceleration that we see here on Earth. Right? And to get that, what we do is we see that weight in imperial units is equal to mass times the actual gravitational acceleration that you'll see, that's g, divided by the gravitational acceleration you would see here on Earth, and that's g sub c. Right? So we're going to check this out in the equation because I know that by doing that, I can sort of see what the units of g sub c should be. Right? So I know that this is going to end up as weight. Right? So weight is going to be equal to mass, whose units are going to be in pound mass, multiplied by some fraction. Right? Now the numerator in my fraction is a gravitational acceleration, so it should be in units that look like feet per second squared. Right? Now, in order to end up with pounds force on the right-hand side of my equation here, I need to have GC to have some kind of funny units here. Right? So the units of GC, it's an acceleration, but it's kind of a special acceleration that has some weird units to make the math work. Right? And the units are going to be pounds mass times feet divided by pounds force per second squared. And we can see why that is. So if we did sort of a unit analysis here and we start to cancel things out, so I have pounds mass here in the numerator and in the denominator, they cancel out. My feet in the numerator and the denominator cancel out. My second squared in the denominator and the denominator of the denominator cancel out. Right? And what I'm left with here is now 1 divided by 1 over pounds force. Right? So when I flip that pounds force up to the top, I get that pounds force is equal to pounds force. Right? Now I know you might be sitting there thinking, man, why are we even talking about this? Right? But trust me, as we start to deal with imperial units and we move through this class, this is going to be very important when you get units that are talking about weight. So please trust me when I tell you that it's going to be really important to understand this. So that concludes our first pre-lecture for thermodynamics, and I'm looking forward to seeing you after a couple of these and we move into real-time lectures. Thanks.